Today? I don't know, really. Just the usual day. It's just end of the week. The winds? I'm not sure. I haven't been outside today. And my cat's right here. That's why I'm looking over in that direction. Oh damn, that's crazy. Oh wow, dang. Yeah, I have not noticed anything of the wind at all. Now, I don't know if it's just windy or just I just don't just don't notice it here. Okay, it's 4 o'clock, so let's go ahead and get started. Oh dang. All right, so good afternoon, everyone. How's everyone doing today? Good, good. Yeah. Hopefully you guys are safe from the winds. It seems like it's pretty bad out there. Yeah, stay safe out there, everyone. Okay. So the plan for today is we're going to start our new, really start our new set of lecture notes in earnest here, which is on strong and weak forms. And so we're kind of turning the page onto a new section of this class, which I like to think about as like general finite elements. And so, just like we mentioned before, everything we've done up to this point is more called direct stiffness method. So direct stiffness method, I like it because it's, I think for a lot of you guys, it's familiar to what you've probably covered in your statics class, but kind of seen from, we kind of set up the problems in a slightly different way for finite elements. And, so we're going to build on a lot of that information there. So, this whole concept of element stiffness matrices, assembly, boundary conditions, all of that's still going to come back. But now we're going to see, how codes like ANSYS actually implement their codes. Okay. And so it's going to take a few weeks, and so it takes a little bit of time to build up this this theory, but afterwards, what I'm hoping is that you'll be able to look at this and see, this is the reason why we can solve so many different kinds of problems with finite elements, and why it's such a powerful method that's that's really risen in power quite a bit, over the last few years. Okay. Okay, so besides that, there is a new homework that's posted. So homework 3 is posted on Canvas, and so homework 3 will give you more practice with truss and beam problems. And so it's shorter, so it's not nearly as long as the second homework, but it's still fairly lengthy. So definitely you get started on it as soon as you can, and that's going to be due next Friday. Okay. And so next Thursday, what we're going to be doing is we're going to be doing our next ANSYS activity. So I didn't want to have those two overlap too much, but I do want it to be due sometime before the midterm, because the midterm is going to be the week after next. Okay. Okay. So are there any questions that I can answer before we get started today? Okay. All right. So there's no questions. Let's go ahead and get rolling. Okay. Turn on stylus. Okay. And so just like we just mentioned, we're starting a new kind of unit on what I like to call general finite elements. Right. And so, I will say that I might be the only one that gives it this name of general finite elements. So if you look up, finite elements like on Google or something like that, people call this just plain finite elements, right? And so, everything with the direct stiffness method that we've been learning, that's kind of a nice educational tool, but it's not really what's used in practice when people think of finite elements. Okay? It has a lot of really strong similarities, and that's why I included it in this class. But in reality, finite elements is goes way beyond that. Okay? Because the real power of finite elements is that it can solve any arbitrary or almost any arbitrary boundary value problem. Okay. And if you remember from last time, we talked about what a boundary value problem is, right? And so boundary value problem has three, I like to call three components to it, okay? Yeah, this is note 6. Yep, note 06. So there's three components to a boundary value problem. And so first of all, you need your domain, okay? Okay. And so remember, for most practical cases where you're using like a software like ANSYS, you're usually going to get your geometry from some kind of CAD software. And so a lot of times this is SolidWorks. So I think that's the one that, is taught mostly and is used a lot in practice. There's also CATIA. So any kind of software that you can use to CAD up your geometry, that works for that. And then what you'll usually do is you'll take that geometry and you'll import that into, your finite element software, which is ANSYS. Okay. All right, so the next thing that you need is you need your governing equations. Right. And these define, the physics of your situation, right? And so for all the problems that we'll consider with finite elements, your governing equations are going to be differential equations, right? And so they can either be ordinary differential equations, or most commonly, in 99% of practical cases, they'll be partial differential equations, okay? And that's where finite elements really, shows its mettle, because usually, if you try to solve a partial differential equation by hand, it's usually too difficult for you to do. So you need to rely on a computer to do that for you. Okay? All right. And then the last aspect of the boundary value problem that we talked about was the boundary conditions. Okay. And so the boundary conditions, remember what they define, or they define any of the loads and constraints that are acting on the exterior of your domain. Okay. And so, if you have an engineering problem where you have all these things, then then you can classify it as a boundary value problem that you can solve with finite elements. Okay. All right. So for the next, couple of weeks, or I would say for today and on Monday, we're going to focus mostly on the governing equations. Okay. Because the thing with finite elements, and if you compare this to some other methods out there for solving computational problems, finite elements is very particular about how and what form that you have to put the governing equations in. Okay. Okay. And so what I mean by that is, we're going to have to take our differential equations and kind of massage them a little bit in order to get them to a form that finite elements can use. Okay. And so, the subject for today's lecture and on Monday is this idea of, two different forms for a differential equation. Okay. And so on the one hand, we'll have a form called the strong form. Okay. And on the other hand, we'll have, the same problem, but we'll formulate it in a different way called the weak form. Okay. Right. And so before people start getting conceptions about these two forms, I'm gonna nip this in the bud. Okay. And so whoever named these different forms it has to rank up there with probably one of the worst naming conventions in all of engineering physics. Okay. And so even though they're called strong form and weak form, this doesn't apply that one is better than the other one. Okay. And so, both of them are the exact same problem, and you can solve them and get the exact same answer. They're just different ways to pose the problem. Okay. It's just one of them is called strong form and the other is called weak form. But, the strong form isn't better than the weak form at all. They're exactly the same. Okay. All right. So generally when you learn about ordinary differential equations, maybe in a previous math class, you most likely work with the strong form. Actually, I'm positive you work with the strong form because I've taught some of those previous math classes. Okay. And so what's going to be new for you guys is actually going to be the weak form. Okay. Right. And you know, and so we're going to spend some time today talking about how do you get the weak form from the strong form, okay? And it's actually, you know, finite elements, when you actually go put it into code, it actually works off the weak form of the equations, not the strong form, okay? And there's a lot of good reasons why it does that, and we'll kind of cross that bridge when we get there. But the weak form has a lot of really nice properties that that lends itself well to, you know, to finite element problems, and that's the reason why we work off that one, okay? And so, you know, the way today is going to progress is we're going to talk about you know, two different specific types of equations. And so we're going to first work on elasticity equations, and so those will be like the equations you would solve in static structural, okay? And so we'll first present the strong form of those equations and then talk about the weak form. And then probably on Monday, we'll talk about a different application, which is heat transfer, okay? And so we'll talk about the heat transfer equations, we'll present them in the strong form, derive its weak form, and then we'll talk about how to solve those kinds of problems, okay? All right, so there are any questions on this before we jump into 1D elasticity? Okay. All right, and so let's start jumping into it. Okay. All right. So where we're going to start is we're going to start with the 1D elasticity problems.
I had a question in chat.
Sure. Oh, question. Oh, sure. Yeah. So I haven't really given, you know, it stated exactly the difference between strong form and weak form yet. So and so we'll see that as we go throughout the lecture today. Yeah. But the only thing I want you guys to remember is that they're exactly the same. They're the same problem. They're just presented differently. And so the strong form and weak form, one is not better than the other one, even though their names strongly imply that. The naming convention is terrible. But so, you know, even though, you know, you'll see when you see the strong form and the weak form, you'll probably think, how are these two the same problem? But trust me that they are. Yeah. Mm-hmm. All right, so let's start with the 1D elasticity problems, right? So I start with this one because this is kind of most similar. This is most similar to, you know, what we've been using ANSYS for up to this point, okay? And so this is basically what mimics what's going underneath the hood for static structural, okay? Okay. And so when we do our ANSYS activities and we choose static structural for our physics, you know, we're implicitly, you know, choosing this kind of equation for, you know, to solve. Okay. And what's unique about these equations, if you kind of remember from our first activity, is that our primary variable of interest is we want to solve for the spatial distribution of displacement. Okay. Because in a lot of these situations, you know, we have some kind of structural member. We're going to apply loads and constraints, and we want to see how that structure is going to deform in response to those loads. Okay, and so I'm going to start with kind of a very simple situation, which is just 1D. Okay. And so it's going to look familiar. So it's going to look like, you know, the problems that we've been working with, you know, for the last few weeks. But we're going to come at it, you know, we're going to come at it from a differential equation standpoint. Okay. Right. So let's say that we have a truss element. Okay. Below, and we'll say it's fixated to the wall on the left. Okay. And on the left-hand side here, we're going to apply a load. Okay. And in particular, we're going to apply a pressure load. Okay. Right. So this T bar right here is going to be an applied stress. Okay. All right. So that's kind of the same thing as, you know, we're applying a pressure on our, you know, on our structure. Right. All right. So in addition to this, we can have a body force. okay? And so body force is nothing more than a force that the structure feels that's, that's felt all throughout the structure, okay? And so a good, a primary example of a body force would be gravity, right? And so gravity, is a force that's felt throughout your entire body, right? Because it acts basically on all the individual particles, right? And so another example of a body force could be like an electromagnetic force, right? And so if you're in like a magnetic field, then you have a force that's kind of pulling you along with that field, okay? All right. And so let's go ahead and define our axes here. And so let's say that on this left-hand side, we'll call this x is equal to 0. And then we'll say that the truss element itself has a length of L, okay? In addition to this, we also have its material properties, okay? And so remember, when we were talking about truss elements, we also need to know its Young's modulus and cross-sectional area, okay? Okay. All right, so Young's modulus will be given by capital E, just like before. Okay. And then cross-sectional area will be A. Okay. And notice here that I've defined these as functions of X, okay? And what we're doing is we're allowing for these properties to change as a function of space, right? And so maybe you might have a bar here that's changing in cross-sectional area. And so maybe it's tapering to like that, right? Right. So with the direct stiffness method, we couldn't handle these situations because in direct stiffness, we assumed that the cross-sectional area was the same all throughout the bar, okay? But when we're talking about the differential equation, we can handle these kind of more general situations. Okay. And then one more thing before we start formulating the equations, let's give these units for B of x, and the units for this will be force over length. Right. Okay, and so what we'll be able to do is we'll be able to take the situation and derive a differential equation for it, okay? From which we can solve for its displacement. Right? Okay, any questions on this so far?
No questions.
Yep. What's up?
I just said no questions.
Oh, no question. Okay. Okay. And so in order to formulate our differential equation, what we can do is we can form a force balance. Okay? In particular, we're gonna perform this force balance on a tiny segment of our bar. Okay. Okay. And so if we look at the bar like this, okay, let's take just a small segment of it. Okay. And so our small segment is going to look like this. Okay. And we'll say that it has a length of dx. Okay. And it also is exposed to some forces. Okay. And so on the one hand, we have the body force. Okay. And we also have the normal forces. Okay. So we have a normal force like this. Okay. And a normal force like that. And we'll assume that it takes those directions just like that. Okay. Right. So those normal forces, you can think of them as internal forces that are keeping this segment in static equilibrium, right? Because remember, we're doing a static structural equation here, so everything is in static equilibrium. All right. Okay. And so what you can do here is we can take all of these forces and we can sum them up and set them equal to 0. Okay. And so what we have here is we have a minus nx, n of x, on the left-hand side, okay, we have a positive n of x plus dx. Okay. Notice that I'm adding dx to these guys because they're, they're at different x coordinates. Okay. And so that's why we have a minus nx right here, which is, where we're saying, that's where the x coordinate is x. And then we move to the right side of the segment, we have n plus dx. Okay, so that's why I've kind of put those functions in there. Okay. And for the body force, we're evaluating this in the middle of the segment. And so that's why I call it b at x plus dx over 2. Okay. And then in order to transform this body force into a normal force, what I'm going to do is I'm going to multiply this by dx, right? Because remember, the units for b is force over length. And so in order to transform that into a force, we have to multiply by a length, which is dx. Okay. Right. So let's take this expression here and let's divide it by dx. Right. And so we have n x plus dx minus n of x divided by dx plus b of x plus dx over 2 is equal to 0. Okay. Right. And if you remember back from probably your very early calculus classes, you'll probably see that this, we're starting to get to the forms of a derivative here. Okay. And so what we're going to do is we're going to take the limit as dx approaches 0. Okay. And so what that does is that for this first term with all the n's, this turns into dn dx, okay, plus b of x is equal to 0. Okay. And so what we have right here is we have a differential equation that describes the static equilibrium of this beam. Okay. All right. Any questions on this so far? Okay. All right. So we have a differential equation, which is great, but right now it's not really in a useful form, right? Because right now we have n here, which is our primary variable, but we don't really want to solve for n most of the time. Because remember, most of the time when we solve these equations, we're interested in solving for displacement. Okay. And so we're going to make substitutions for n right here in order to get us that. Okay. And so for the first substitution, I'm going to substitute n is equal to a of x times sigma of x. Okay. Where this sigma of x right here, this is the internal stresses within the structure. Okay. So whereas n is a internal force, then all I'm doing here is I'm converting that to an internal stress. Okay. And so in order to do that, you have to multiply by area, because stress is a force over area. And so when you multiply by area, then you get, force from that. Okay. Okay. And then in addition to that, I'm going to make another substitution for the stress, where we can use Hooke's law here. Okay. And so we can say that stress is equal to Young's modulus of x times strain. Okay. And so this right here is Hooke's law. Okay. And so we can plug that in for n of x up there. And so we're getting warmer here. And so the last thing that I want to substitute here is for the strain. Okay. Because the strain epsilon of x is equal to du dx, right? Where u right here is the displacement of the bar, okay? And so, if you kind of remember from your previous solid mechanics classes, we can express strain as the spatial derivative of the displacement of the bar, okay? Right. And so what we can do is we can make all these substitutions here, and we can arrive at the at our final differential equation. Okay. Okay. Any questions on this before I go ahead and plug everything in? Okay. Okay. And so if we make all those substitutions, we end up with the following equation. Okay. And so we have d dx of e of x, a of x, du dx, right? And so all of that is this is all the result of making the substitutions for n of x, okay, plus b of x is equal to 0. Okay. And so what we have right here, this is the strong form of the 1D elasticity equations. Okay. Right. And so in other words, this is our governing equation. And so, we did this kind of, relatively quick derivation here to show that, this governing equation, even though it's mathematically, it's a differential equation, what it represents is, the force balance and the static equilibrium of kind of every point inside our structure. Okay. And so when you're working in ANSYS and you pick static structural, ANSYS underneath beneath the hood, beneath what you can see, ANSYS is basically loading in an equation like this. Okay. And of course, ANSYS, they're loading in the 3-dimensional version of it, but it's essentially the same thing. Okay. Okay. And so so that's our governing equation. And so now let's talk about our boundary conditions, because we had two that we had displayed in our structure. Okay. Okay. And we need boundary conditions because, as you can see from the equation right here, what we have is a second order differential equation, right? And so we have one derivative out in front, and then we have another derivative right here. And then when you combine them, you end up with a term with a second derivative on the displacement. Okay. And so in order to properly solve this differential equation, we're going to need two boundary conditions that we're going to apply. Okay. All right. So first, let's talk about the boundary condition on the left-hand side, which is the applied traction. Okay. Right. And so an applied traction boundary condition, this is essentially the same thing as a load, right? Right. And if we connect this to, what we were discussing before, with our trusses and beams, this is our Neumann boundary condition. Okay. And so the way that we apply this boundary condition to this equation is like the following. Okay. And so mathematically, it looks like this. Okay. Basically, what we're saying is that at x is equal to 0, the stress on the truss has to be equal to the applied traction. Okay. And so if we look back on the previous page on our formula for stress, right? We know that sigma of x is equal to E of x du dx, okay? Right. And so what this boundary condition is saying is that sigma at x is equal to 0 has to equal to, in this case, we'll use a minus t bar, okay? Where t bar, remember, that was our applied stress, right? And so if we apply this to, we plug in our equation up there for stress, what we say is that minus t bar here is going to be equal to E of x du dx, okay, at x is equal to 0. Okay. And so basically when we apply this boundary condition, we're going to take our displacement solution du dx, right? Take the derivative of it, plug in x is equal to 0, multiply by the Young's modulus, and then set that equal to the traction. Okay. Any questions on this? Okay, so that's the applied traction boundary condition. So that's basically applied or conceptually the same as our load. Okay.
Professor,
Yep. What's up?
could you go back real quick?
Oh, sure. Okay. So this is the same as our load. Okay. And so if you think back to our truss and beam problems, we had another type of boundary condition that we applied, which was the constraints, right?
Okay, thank you.
Yep. Good. And so the constraints, remember what they did was they put constraints on the displacements. Okay. Okay. And so the fixed constraints basically forces the displacement to have a certain value, which most of the time is going to be 0. Okay. Okay. And so mathematically, the way that we can apply this is that we can say that U, where U is our displacement solution, okay, and we evaluate this at x is equal to L, we say that this is equal to 0, okay? And in terms of mathematical terminology, this is the same as a Dirichlet boundary condition. Okay. Right. So now that we have our governing equation, we have the mathematical formulation of the boundary conditions, and implicitly, just by drawing the picture, we also have our domain. We can form the full boundary value problem for 1D elasticity. Okay. Okay. And so this boundary value problem is for the strong form of 1D elasticity. Okay. And so remember, we need 3 things for our boundary value problem. So first of all, we need our domain or geometry. Okay. And so, one way that we can describe the geometry is we can draw the picture again, or we can simply just define, the values of x. Okay. Okay. And so since our x values here go between 0 and L, what we can say is that our domain here is going to be 0, which is less than x, which is less than L. Okay. Next, we have our governing equation, which we listed before. Okay. And so our governing equation is d dx of e of x, a of x, du dx plus b of x is equal to 0. Okay. And so remember, that was our differential equation that we got from performing our force balance. Okay. Okay. And then the last thing that we have is our boundary conditions, which we just found out here. Okay. Okay. And so our boundary conditions, our first one, which I'll call boundary condition A, was our traction boundary condition on the left-hand side. Right, so we have E du dx at x is equal to 0. This is equal to minus t bar. Okay. And then our second boundary condition is u of L is equal to 0. Okay. And so these trio of things right here basically give us the strong form of our boundary value problem. Okay. So remember, you need all three. Okay. All right. Any questions on this before we do an example? Okay. Oh, question? Oh, okay. So, these problems in this form, we can actually solve a lot of these by hand because they're just ordinary differential equations, okay? And so we're going to focus mostly on 1D problems at first because we can kind of solve them by hand. But in reality, of course, you wouldn't use finite elements and you wouldn't use the software to solve these 1D problems. But it's a nice launching point for the theory because a lot of the 2D and 3D problems, even though the math for them is a lot more complicated, it builds on a lot of the similar ideas. Okay, and so let's do an example where we actually solve a 1D boundary value problem for an elastic structure. Okay. And so let's say that we have the following structure. Okay. And so let's say that we have a structure like this. Okay. And so it's just it just consists of a single truss beam or truss bar. Okay. And on one side we have a pin support, and on the right side we have a roller support. Okay. And we'll say the length of the truss element is 1 meter. Okay. And then on the right hand side here, we're gonna pull it with a stress of 100 pascals. Okay. And so let's define x is equal to 0 on this side. We'll call this x is equal to L on that side, where L is equal to 1. Okay. And let's define its material properties. And so let's say that the bar doesn't have any spatial variation of Young's modulus or area. So let's say that the E is equal to 100 kilopascals. Okay. And the A here is going to be 0.1 meters squared. Okay. All right. And so given all this information, let's set up the boundary value problem. Okay. And we'll set it up in the strong form, and then we'll also solve for the displacements. Okay. All right. Any questions on the problem setup here? Okay. So let's go ahead and set up our boundary value problem, right? So we need to establish our three things, right? So first, let's set up establish our domain. Okay. And so our domain here is since it's just a 1D problem, we just need to establish, what values of x that we're going to be looking at. Okay. And so our x here is going to go from x is equal to 0 to x is equal to L. But since, we know the value of L in this case, our value of L is going to be 1, then we can say our domain consists of the values of x that are between 0 and 1, okay? And so mathematically, we can express this as 0, which is less than x, which is less than 1, okay? Okay. Next, let's establish our boundary conditions. Our governing equations. Sorry, my mind was ahead of my of the rest of everything else. Okay, and so since we have a 1D elasticity case, we're going to write out the differential equation for elasticity. Okay. Okay, so that's going to be d dx of E times A du dx, okay, plus b of x, and this is equal to 0. Okay. All right. And so at this point, we can actually simplify this equation for us because we know a lot about the problem. Okay. And so first of all, not the problem didn't say anything about any body force, so we can just go ahead and cross this out. Okay. All right, so we're going to eliminate that from the equation. Okay. Next thing that we can do is, because E and A here are constants, right? Then there's no need for us to take derivatives of them. And so let's go ahead and pop these guys out, okay, because they're constants. And so there's no need to do any kind of chain rule or product rule or anything kind of crazy like that, okay? Right, and so when we do that, what we have is E times A times d dx of du dx, okay, is equal to 0. Right. And then from here, what we can do is, because E and A are constants, we can just go ahead and divide both sides by that, okay? Okay.
I have a quick question.
Sure, what's up?
So if gravity is a body force, so why are we allowed to just say there's no body force here?
Yeah, no, good. That's a great question. So gravity is a body force, but remember, gravity force acts vertically. In this case, we're looking for the displacement in the horizontal direction, and so that's why in this case we're going to ignore gravity, because it doesn't affect our displacements in the horizontal direction.
Okay, I see. That makes sense. Thank you.
Yep. And in other cases too, even for vertical problems, you'll see us ignore gravity as well. And that's usually because of a scaling argument, because even though gravity is always present, a lot of times and say that you're considering a vertical situation, your vertical loads are going to be much higher in magnitude than whatever is going to be applied with gravity. And so gravity is there, but in those cases where your applied load is much higher, you can still kind of ignore gravity and kind of simplify your math a little bit. Yeah, so exactly. So you can say that it's negligible. Okay. And so once we cancel out EA, then all we're left with is d squared u dx squared is equal to 0. Okay. And so that's our governing equation for this problem after we perform our simplifications. Okay. All right, any questions on this? Okay. All right, so now let's establish our boundary conditions. And so this step is important. And so, after this example problem, we'll be focusing on the governing equation. But when you're setting up your boundary value problems in general, I really want you to pay attention to the boundary conditions, because those make probably the most impact on the results in the end. And I especially want you to be careful, because the derivation that we kind of did, right before this example, we did those for a specific set of boundary conditions, right? And so if you remember from the derivation, we had a traction boundary condition on the left and a fixed boundary condition on the right, okay? In this example, it's opposite. And so in this example, we have our fixed boundary condition on the left at x is equal to 0, and then we have our traction boundary condition at x is equal to L. And so we need to make sure that we apply that, okay? All right, and so first thing, let's apply our fixed boundary condition. Okay, and from our diagram, for this example, we know that the fixed boundary condition is being applied at x is equal to 0. Okay, and so mathematically, what we can do is we can say u at x is equal to 0 is going to be equal to 0. Okay. So does that make sense about why we did this at x equal to 0, not x is equal to L? Yep. Okay. All right. So now we have our traction boundary condition, and then this traction boundary condition is being applied at x is equal to L. Okay. And so what we're going to do is going to take E times du dx at x is equal to L, which in this case is going to be 1. And this is going to be equal to our traction. Okay. Yep. Yeah, so exactly. So yeah, we apply our fixed boundary condition at the left because that's where our pin support is. Okay. And so mathematically, what for the traction boundary condition, we can say that E times du dx at x is equal to 1 is going to be equal to 100 pascals. Okay. And in this case, we leave it positive because this this traction boundary condition is tensile in nature. Okay. And so that's why we leave it like that instead of, making it negative like we did in the previous derivation. Okay. Okay. And so now that we have our governing equation and we have our boundary conditions, we can go ahead and solve this guy. Okay. And so luckily for us, our governing equation here is fairly simple. And so we just have the second derivative equal to 0. Okay. And so what we can do is we can just integrate this guy twice. Okay. And so we take the integral once, and so what we get is du dx is equal to C1, okay? Because we take the integral of 0 is just 0, but then because we're performing indefinite integrals, we have to add our arbitrary constant. Next, we're going to take the integral again, and then what we get on the left is u of x is equal to C1x plus C2. So pretty straightforward. So it's just a simple integration of 0. Okay. Okay. And so now that we're at this point, we can go ahead and apply our boundary conditions. Okay. And so first, let's apply our fixed boundary condition because that's the simplest one to do. Okay. And so we do u of 0, and that's going to be equal to 0. Okay. And so we plug in x is equal to 0 into our expression right here. So we have C1 times 0 plus C2. Okay. And that has to equal to 0. And so what that tells us is that C2 is equal to 0. Okay. Okay. And so that's our fixed boundary condition. And so now let's apply our traction one. Okay. And so our traction boundary condition is what we have up there. Okay. So we have E times du dx evaluated at x is equal to 1. And this has to equal to 100 pascals. Okay. And so if we plug in from the problem, we know that E is equal to 100,000 kilopascals. Okay. Or is 100 kilopascals, sorry. Okay. And then du dx here is just going to be C1, okay, because that's what we got from this equation right here, right? And so what we get is 100,000 times C1 is equal to 100 pascals, okay? And what we get is C1 is equal to 0.001, okay? And so now that we solve for C1 and C2, then we can plug those into our solution, and then we get our final answer for u of x. Okay. Okay. So any questions on this before we write out the final answer? Okay. So let's go ahead and write it out. Okay. And so our final answer in this case is going to be just simply u of x is equal to 0.001x. Okay. And if we graph this, we can see that it's just simply a linear function. Okay. So it looks like that. Okay. Where this is x is equal to 1. And then this value up here is 0.001. Okay. All right, so that's a strong form of the equation. So, when we're working in 1D, we can actually solve these by hand, which is nice because then that actually gives us a way to assess our finite element solutions. Okay, and so probably not next week, but the week after that, we'll talk about how do we actually form finite element solutions to these problems. Okay? And having the exact solution is actually really useful then, because then what we can do is we can assess, how well did our finite element solution perform compared to the exact one. Okay? All right, so but before that, let's go ahead and move on, and let's move on to the other form of these problems, which is the weak form. Okay. And so remember what I said before. So a weak form is not, it's not bad. And so there's nothing wrong with the weak form of the problem. It's just a different way to formulate it. Okay. And so whoever named this, I can understand why it's named like that. But the bad thing is the reason why it's called the weak form involves, talking about a lot about the mathematics of the problem, where it gets really complicated and sophisticated. So if you kind of understand that, then it kind of makes sense why someone picked it. But when you're first learning about the strong form and the weak form, you always have to go through this explanation about there's nothing wrong with the weak form. There's nothing inferior about it. It's just, it's just a different name. Okay. All right. And so the starting point for our weak form is actually going to be our governing equation. Okay. And so our strong form governing equation, if you kind of remember from like literally 10 minutes ago, was this. And so we had d dx of e times a du dx, okay, plus b of x is equal to 0. Okay. Okay. And so this was our strong form of the equations right here, right? And so what we're going to do is we're going to massage this a little bit, and we're going to do some weird stuff. So I will admit that a lot of the things that we're going to do to this equation are you're going to ask yourself, why in the world would we actually do that? Okay, but in the end we're going to get a different form of this equations that the finite element method actually works on. Okay. Okay. So the first thing that we're going to do. So right off the bat, we're going to do something really strange here, is we're going to multiply this entire equation by an arbitrary function. Okay. Okay. And so this w of x here is just an arbitrary function, right? And arbitrary means it can be anything. Okay. So we're going to take, a function that we don't know anything about, and it could be anything, and we're going to multiply that by our entire equation right here. Okay. And so yes, it's weird. Okay. So like, how can, it seems like we're getting farther away from a solution because, solving this differential equation is already, kind of an ordeal, right? But now we're multiplying this by another function that we don't even know. Okay. And I'm expecting you to kind of believe that this is helpful. Okay. And so I know it doesn't seem helpful, and I know it seems weird, but just kind of trust me a little bit. Okay. All right. And so let's put some requirements on this arbitrary function, because it can't really just be anything. Okay. But what you'll see is that the requirements here are fairly weak. Okay. And so the only requirement that we're going to specify is that wherever we have a fixed constraint, then the w function has to equal to 0. Okay. Okay. And so basically what we're saying is that, if we consider our problem domain and our boundary value problem that we're considering, right? Whenever we have a fixed constraint or a Dirichlet boundary condition at a certain location, right? So whether it be x is equal to 0 or x is equal to L, okay? So either one of those, then the W function has to equal 0 there as well, okay? Right, so basically what you have is you have either W of 0 is equal to 0 or W of L is equal to 0, okay? And it depends on your problem. So it depends on where your fixed boundary condition is. Okay. Okay. Any questions on this so far? Okay. All right. And so that's the first step, defining the weak form. So first step is to multiply by random function. Okay. The next step, which is also like a, why would you do this step, is we're going to take this entire equation and we're going to integrate it. Okay. Right. And once we do this, we're going to have a big long integral expression. Okay. And so what I'm going to do here is, because once this w of x distributes through, it's going to distribute to both the derivative term and also b of x. And so I'm going to separate those two guys out into separate integrals. Okay. All right. So let's go ahead and do that on this page. Okay. And so for one integral, we have integrals from 0 to L of w of x times ddx of EA du dx dx. Okay. And so that's our first integral, which was our arbitrary function multiplied by our derivative. Okay. And then next we have integral from 0 to L of w of x, b of x, dx. Okay. And all this is equal to 0. Okay. Okay. So we're getting farther and farther away from a solution. Okay. All right. And so, at this point, we have our two integrals here, but I just want to focus on this guy for now. Okay. Because the integral with the b of x function, remember b of x is our body force, there's really nothing more we can do with that function, because, w of x is arbitrary, b of x can be kind of anything. And, we just kind of, in the end, we just got to plug it in and integrate it. Okay. It's this function right here with the derivatives that we can kind of work with. Okay. And in particular, I'm going to draw your attention to w of x and also this guy. Okay. Right. And so the reason I circle those two terms is, we have basically two functions that we're working with, right? And so we have w of x and we have u of x, right? Where u of x is eventually the solution that we want to solve for. Okay. If we kind of separate the terms like this, what we can do is we can count the number of derivatives that these functions have. Okay. And so let's start with w of x. And so w of x is just by itself. And so it had 0 derivatives. Okay. Meanwhile, u of x right here, we have one derivative that comes, straight right there. And we have another derivative that comes from outside the parentheses. And so this guy right here has actually two derivatives. Okay. All right. And so, at this point, w of x is looking at u of x and say, hey, that's not fair. How come you can have two derivatives and I have 0, right? And so, what we have right here is kind of an unbalanced situation, right? So we have two functions here, essentially. E and a don't really count because they're physical properties, but we have two functions here, and their and their derivatives are unbalanced. Okay. And so this is not good. And so, what we want to do is we want to balance these guys, and so they have an equal amount of derivatives. W should just be glad to be. Yeah. It's like, you just showed up here. How can you be here and demanding derivatives like that? But that's just how it goes. We have to kind of be fair. So once everyone shows up, okay. All right. And so what we're going to do here is we're going to perform integration by parts so that we can balance the derivatives. Okay. And so anyone who has a younger sibling is probably familiar with this. So, your younger sibling's born and all of a sudden they get all your toys because they're the young one. But okay, and so let's perform this integration by parts, right? And so this is the way I do integration by parts. So in all my time working here for the past couple of years, I've seen lots of interesting ways to do integration by parts. Okay, but this is how I kind of do it. And so what I'm going to do is I'm going to split up this integral into two separate components. Okay. And so one component I'll call u, and the other component I'll call dv. Okay. And so for u, we're going to set this equal to w of x, and then dv is going to be everything else. Okay. It's going to be d dx of ea du dx. Okay. And then what I'm going to do from here is I'm going to take the derivative of u. Okay. And so we're going to get du. And so this is going to be dw dx. Okay. And then we're going to take the integral of v. Okay. Or the antiderivative of v, I should say. Okay. And so the antiderivative will get rid of that d dx. And so what we're left with is ea du dx. Okay. And then to perform the integration by parts, what we do is we take u times v, and then we add them together. Okay. And then we take v times du, subtract them, and then integrate those guys. Okay. All right. And so if we perform that, then what we get is the following, right? And so first we have u times v, and so this is going to be w times ea du dx. Okay. And since this is a term that's already evaluated from the integral, we're going to evaluate this from 0 to L. Okay. And then from this, we're going to subtract integral from 0 to L of duv. And so we have dw dx times ea times du dx. Okay. Dx. Okay. And then we also have our same integral from up here too. Okay. And so, even though we're not doing anything with this integral on the body force term, we can't forget it. So we still need to bring that guy down. Okay. Okay. And so the next step here, what we're going to do is we're going to take this term and then evaluate it at x is equal to L and x is equal to 0. Okay. Because this term has kind of already been evaluated from the integral before. Okay. And so this is we can actually evaluate this guy. Okay, so any questions on this so far? Okay. All right. But to actually evaluate this guy, we have to actually specify what our boundary conditions are, right? And so I'm going to give I'm going to apply this for a specific case. But remember, when you have the weak form, you're not limited to just this case. This is kind of just a methods kind of derivation. Okay. And so for now, let's use this case. Okay, just so that we have a concrete something concrete to plug in for the boundary conditions. Okay. Right, so let's use the case where we had a traction boundary condition on x is equal to 0 and a fixed constraint at x is equal to L. Okay.
Sorry, Professor, when you're done, do you mind going back real quick?
Oh yeah, sure. Let me finish writing this first and then I'll go back.
Thank you.
Right. All right.
Perfect, thank you.
Mm-hmm. Okay. And so we have our traction on the left and then fixed on the right, okay? And so what this tells us is that u of L is equal to 0, okay? And remember our requirement on w, right? And so w, at this point, w is just any random function, but it did follow some rules, okay? And so our rules for w was that w of L is also going to be equal to 0. Okay, so let's remember that as we evaluate that term. Okay. And then our other boundary condition over here is E times du dx at x is equal to 0 is equal to minus t bar, okay? Where we use a minus because it's a compressive force, okay? And so now let's actually evaluate that term that we had there, okay? And so that term was W E A du dx, okay? Evaluated from 0 to L, okay? And when we evaluate this, we get this guy splits up into two, right? So we have one term that's evaluated at x is equal to L, and then we have another term that's evaluated at x is equal to 0, okay? And so what we get is W E A du dx, okay, at x is equal to L minus W E A du dx at x is equal to 0, okay? And so this is just, just evaluating integrals and just plugging in the bounds, okay? Let's look at this guy first, okay? And so when I plug in x is equal to L here, what we get is W of L times E of L, A of L times du dx at x is equal to L, okay? And so when we're evaluating this at x is equal to L, we're basically just plugging in L for every value of x, okay? And remember, E and A can also be functions of x as well. Okay? Yeah. That's one way to think about it. Okay. And so, one thing that should jump out to you here is that we have W of L right here, okay? And we know from our requirements on W is that this W of L is equal to 0, okay? And so what that will do is this will cancel out this entire term right here, okay? Right, so that's nice. And so, our one rule for W ends up, saving us some math. Yep. Okay. And so let's look at the other term, okay? And so the other term right here, we're going to evaluate this at x is equal to 0. Okay, so we have W of 0 times A of 0. Okay, and then I'm going to separate E times du dx at x is equal to 0. Okay. Right. And so I separated those two out because we already have seen what that equals to, right? Because according to our boundary condition, this product of E times du dx at x equal to 0, this has to equal t bar, or minus t bar, okay? And that comes from our traction boundary condition, right? Right? And so now what we can do, so now that we've evaluated this term, we can go ahead and plug it in, and we finished, and with that, we've been able to finish our weak form expression. Okay, any questions on this? Okay. Right, so let's go ahead and write out our weak form, okay? And so our weak form is given by the following. And so first thing we have is our traction term, right? And so we have W of 0 times A of 0 times T bar, okay? And so that comes from, what we just solved for before, right? Next, we have minus integral from 0 to L of dW dx times E times A times du dx, okay? And this is dx plus integral from 0 to L of W of x, P of x dx, and this is equal to 0, okay? Right. And so from here, we also have to remind ourselves of on the conditions on W and U, okay? Where W of L is equal to 0 and U of L is equal to 0, okay? And so what I have boxed right here, this is the weak form for 1D elasticity. Okay. And so it looks worse, I know. So it's not only do we have derivatives here, but we have integrals, and we have a W function that, doesn't make sense at this point. But believe it or not, this is actually the starting point for, a lot of finite element codes. Okay. And so, what's happening under ANSYS is that they're working with basically a form of these equations when they solve it. Okay. And because even though it looks like a mess right now, it actually has a lot of really nice properties, which I'll talk about in a bit. Okay. Okay. And so let's give our W function a name at this point, because at this point we've just been calling it random function, arbitrary function. So let's put some respect on W of x, because it's actually going to help us out. Okay. And so W of x, the formal name for it is it's called a weighting function, or a weight function. Okay. And why that is because it basically is going to help us. You can almost think of it as like balance the weight of the derivatives. Okay. And so the key point of the weighting function is this guy. Okay. Okay. Because remember, where we started, and the reason we did our integration by parts was we had this integral with an unbalanced derivative. Okay. And so now what we have, instead of having 0 derivatives and 2 derivatives, what we have is 1 derivative and 1 derivative. Okay. And so what this basically allows is this allows our derivatives to be balanced. Okay. Okay. Right. And as we all know, if things are perfectly balanced, then that's as all things should be, right? Okay. Because what this is going to allow us to do is that, once we actually work with this in the finite element form, this is going to create element stiffness matrices that are symmetric. Okay. And what it also allows us to do is it allows us to use, much simpler functions to plug in here. Okay. And so, in a bit, in a couple of weeks, you'll find out, why, we make that, why ANSYS gives you a setting to use either linear functions or quadratic functions. Okay. And the fact that you can use linear functions is a direct consequence of this. Okay. Because if we had a situation with second order derivatives, you wouldn't be able to use a linear function. Right? And then once we start working out the math for some of these problems, you'll be very glad that we can use linear functions for these, because linear functions make things, very, very easy. Okay. All right. So any questions on this so far?
So will this material be on the midterm? Because this, I don't know, this seems, how we got here is very counterintuitive.
Right. So this is not on the first midterm. So the first midterm, kind of like what I mentioned on Tuesday, that book is written for that. Okay. And so the starting with this lecture, this is not going to be on the midterm, but it will be on the second midterm. But we can worry about that, much later. And I know right now, a lot of this doesn't really make any sense, and a lot of the steps that I took are fairly arbitrary. But it's like, it's like a book where, a lot of the things that don't really make sense, but kind of once you see the full picture and once we kind of learn everything, then a lot of these things make sense. But at this point, I know, because I've been there too. So first time I saw this in a finite element class, I was like, what the hell is going on? Why are we doing this? This makes no sense at all. So I get it, so I know right now it's confusing, but there's still a lot of material that we need to cover for this. But it's not going to be on the midterm, not yet. Okay. Okay. And so we just have a couple minutes left, and so I do want to leave you with a couple closing points, right? And so I just want to remind you once again that even though this weak form here looks really scary, it's equivalent to the strong form. Okay? Right. And so the strong form of these equations, where we had just the differential equation, that problem and this one are exactly the same. Yeah. All right, question. So the material on homework 2 will be on the midterm. Yes. Yeah. So homework 2, you can think of homework 2 as kind of the cutoff for what's going to be on the midterm. So the homework 2 will just cover up to beam equations. Yep. Okay. And so, even though these equations look very different, strong and weak form are equivalent problems, right? And so if you solve one, then you would get the same solution for the other one as well. Okay. And so another piece of trivia that you may or may not have covered this in a previous solid mechanics class is that this form of the equations right here, you can get the same form through the principle of virtual work. Right. And so if you're kind of familiar with that principle, then you kind of arrive in the same point, except the interpretations of the different terms is different. So I think in virtual work, I think your W function there is kind of like either a small perturbation in displacements or it's actual like virtual displacements. Okay. And so, this form of weak forms, didn't come just out of finite elements. So it existed kind of in solid mechanics before. Finite element people just kind of took this and kind of built an entire method out of it. Okay. All right. Any final questions on this before we wrap up for the week? Okay. So that's all we got time for today. So thank you guys for tuning in today. I know it was kind of an intense math day, but over the next couple of weeks, what you'll see is we'll work with this equation and actually build finite element methods that are very similar to what's in ANSYS. And so thank you guys for your patience. And remember to start working homework 2. And then next week, I'm sure everyone's excited for we're going to do our next ANSYS activity on Thursday. Okay. So look forward to that. And so have a great weekend, everyone. And I'll see you guys on Tuesday. Yeah.
Thank you. Have a nice weekend.
Thank you.
Thanks. You too. Yeah. Midterm is March 18th. And so not for a couple more weeks. Yeah.
Professor, sorry, can you go back to the last slide again?
Yes. Oh.
Thank you.
Yep.
Hey, Professor, really quick.
Yep. What's up?
So I emailed you 2 days ago. If it's my homework's late, do you want it still through Canvas or do you want it through email? Just through Canvas still?
Yeah. So if you can still turn in through Canvas, that's what I would prefer because it it kind of organizes everything for me there. But if it's closed on Canvas, you can just email it to me, and then that's fine as well.
Oh no, I think I can submit on Canvas. Sounds
Okay.
good. Thank you.
Yep.
Cool. Bye.
Bye.
Thank you.
Haley, Jasmine, did you guys have any more questions? Okay. Okay. Yeah. So have a good weekend. I'll see you guys next week.